Now, after I have introduced the Euler's numerical method for solving the initial value problem of this kind, here is the governing equation. Y derivative equals a certain function that depends on t and y. So this equation is subject to an initial data, y at certain t, which we denote by t naught. Y at t naught is equal to y naught. So we want to solve this initial value problem using a numerical method. And the simplest method is Euler's method I introduced in my previous video. And we know, okay, let's do a quick review. That is the Taylor series expansion if we truncate from this squared term. And this is the solution curve y of t expansion at t0. But this first two terms will be the linear approximation to the solution curve. So that will lead to the Euler's method because the derivative, which is given, right, the y prime is simply the f. So we can put the f value here at t0, y0. So in the step one, immediately we get this approximation. It's actually a linear approximation. So after truncation, this will lead to the local discretization error. We abbreviate as LDE. L means local, D is discretization, E means error. So LDE. So this it's because of the truncation, right? So this becomes the approximation. So we use a straight line approximation to the curve y. When we assume we try to calculate the y at the solution at t1, then the solution at t1 is approximately this quantity, and we denote it by y1. So y1 is computed from the y at t0, right? y0 plus this one step says f at t0, y0. So this certainly this y1 is an approximation, and this approximation is due to the truncation. So we call it local discretization error. For Euler's method, the local discretization error is of order h. And so let's imagine if you continue with this implementation, and we know the Euler's method. Okay, we repeat this minor. So from y1, from t1, y1, we can get y2, etc. So we get a general formula. That is, we can always calculate the next y value using the current t and y value. So in step one, suppose the initial data is exact, then due to the truncation error, we have local discretization error. But if we repeatedly use the Euler's formula, and in the next step, we can see the y1 is already an approximate value. So we're not using an exact value. That means it's already approximate y1 to calculate y2. This is different when we calculate the y1, right? Because we started with exact value y naught. So when we proceed in this way, then the errors will accumulate. So local discretization error at each step from the truncation, also from the errors, because we're not using exact y values at each tj. So this will get the cumulated global discretization error. So we denote it by GDE, global discretization error. So for Euler's method, actually the global discretization error is also order of h. That means it can be estimated in using h. So let's compare. Suppose we look at two methods with different h, because we have seen different results for this specific example with the right-hand side function being depending on t and y, in such a way, right? It is t minus 2y, initial data is at when t is 0, y is 1. So we can actually solve this linear equation to get exact solution. And we can also use the numerical method to calculate numerical solution of the above problem. So if we use Euler's method, and if we use step size h being 0.2, so then we proceed this way. Each is so in the first step, so you get the y value at t1. So we proceed with the step size being 0.2. So 0.2, 0.4, 0.6, and then we get the corresponding y values at 0.2, at 0.4, and y value at 0.6. So you can continue, right? At each step, you just continue. You can get more and more y values. But each step, assuming even if your initial condition is accurate, but due to the truncation error, you have the local discretization error. But from the next step on, your y value, which is y1, right? From here, so your y1 is already approximate. It's not the same as the exact y value at this point 2, t1. So at the t1, your y1 is different than the true value. So that is already the error from the start. And then apply the linear approximation, which is that Euler's formula. That formula, that's because of the truncating the higher terms in the Taylor series. So that's going to lead errors in the next step. So this, when we look at the y2, which is 0.4. So this y2 is different than the exact value y at t2. So this error is caused by the truncation error using Euler's formula, also caused by the y1, the approximate y1 value. So with this step by step, and when you get to the third step, so the error, local discretization error will accumulate. And then we have the global discretization error. So if you repeatedly calculate after many steps, and you will notice global discretization error. So using this example, we can see for this initial value problem, and the solid line being the exact solution. And then we have approximate solutions when using step size 0.2. So that's the very low curve when use the step size 0.2. Right, that's the y1, that's the y2, y3, y4, y5. In 5 steps, we get the y value at this t, when that's t is being 1, and then continue. So you proceed with that step size 0.2. And what if you decrease the step size, make it smaller? For example, we use 0.1. When the step size is half as big, half as before, and then we notice a better approximation to the true solution. So you see this curve, with more calculations because proceed with 0.1. As a matter of fact, a global discretization error, if we compare H2, suppose this is our H2, the step size, and previously, let's call it H1, the step size. So when the step size is half as before, and we notice the improvement in the approximation to the solution. So there is this relationship, global discretization error is actually approximately the ratio of H2 over H1. You see, when H2 is a half of the previous step size, so H2 over H1 will be, the ratio will be half. And the global discretization error using H2 compared to the global discretization error using H1 is just that ratio, which is H2 over H1, right? Which is half. It's half. So we can see when you half the step size, the global discretization error is also approximately half as before. So that explains why our numerical solution is better than the earlier approximation when the step size was bigger. So because of that, we can decrease the step size again. For example, make it even smaller than 0.1. So when you use the step size 0.05, then you notice the global discretization error is even better. So with that general trend, the Euler's method can be improved. It is very simple to implement, and also you can achieve satisfactory results if you use a small step size. So here is our precise definition for local error. Local error, that is your numerical result at a certain TJ, right? That's our approximate Y value at TJ. This is the exact solution at TJ at this time. And then the difference will be the local error. So that is the local error at a certain time, TJ. If we compare all the local errors, and there is the largest local error. So actually, we can take absolute value. So because sometimes the YJ and YTJ, so we want to measure the magnitude. We do not care too much of the sign, right? So we put absolute value sign for this difference. So that EJ is actually the absolute value of this difference. So global discretization error is the largest possible value of all the EJ. So that is to just compare all the local errors, pick the largest one. That's the global discretization error. So as I already commented, that global discretization error decreases. And yeah, with that ratio depending on H. So you see approximately when the step size becomes half as before, and you do more steps, and the global discretization error is approximately half as before. And if you make the H, the step size, even smaller, and then you still see the similar ratio, right? The global discretization error is further reduced. Yeah. So because right now this H is the half of the previous H, so you need to do more steps to arrive at a certain value at T. So then the global discretization error, again, compared to the previous one, is half as the previous one. Okay, so we can see that H plays a very important role to improve the accuracy of the Euler's numerical method. Yes, we can, because of the formula simple, and we can certainly write program to calculate y at each tj, the approximate value yj. So now let's quickly look at other higher order methods. So we will not see all of the numerical methods, but we will look at one-step methods and popular methods that have different accuracy. So let's see the well-known methods such as Euler's method, which is very simple and a prototype of other methods with global discretization error being this order of h to the first power. And there's a midpoint method. It has a global discretization error at this order of h squared. Green's method also with the same accuracy. And Runge-Kutta method of order 4 has this global discretization error at this order of h to the fourth power. As you can imagine, when h is very small, for example, think of 0.1. Think of 0.1. So if you use Runge-Kutta method, the 0.1 to the fourth will be much smaller compared to this number, right, 0.1. So that means the Runge-Kutta method has a very accurate result. But that means the several methods, and you're getting more and more accurate from Euler's method to midpoint to Huygens method to Runge-Kutta method of order 4. So more and more accurate. Yeah, so that's what this table says. But more work will be involved in order to achieve that high accuracy. So let's look at midpoint method. So the midpoint method, if we look at the algorithm, it is actually first you evaluate the function. Recall that we're focusing on an initial value problem of this form. So this is a first derivative of y equals f at ty. F is some function and with some initial data. So this is the initial value problem we're solving. And first of all, we just see one step. Let's imagine just one step. Suppose I have tj to tj plus 1. So when j is 0, that's the first step, right? From t0 to t1. But the thing, in one step, what it's doing is that you get using this tj, that's the y value, no matter it's a precise y or approximate y. So use the t1 y1 to get the slope. And then, so this is a one first time evaluation of the slope function. And then with that slope, you go half a step. You see, you go half a step from this tjyj and go from using that slope. Suppose this is our slope. And you go this way, go to the half, because this overall it is h. So therefore, this is half of h, half of h. So this half a step, this is a totally Euler's method. So we recognize that that is the Euler's method using half step. And then that allows you to get the y, approximate y in the midpoint. So we are going to write, this is a y at j half. That's the y at the midpoint of the interval from tj to tj plus 1. So at this y at midpoint, then we evaluate the slope function again. So this is our tj plus half of h. So using that tj plus half of h, and using this y, which is same as the right-hand side, right? We write this y. Then we get slope at the midpoint. That's why the method is called the midpoint, because using the slope at the midpoint and starting from the draw. So suppose using this midpoint, we can figure out a slope. So then, but we pass through the first point using that slope. We construct a line that is using the slope of the midpoint at the midpoint. And pass through the beginning point, which is the tjyj, the beginning point. Then we draw this line. This is the last to arrive at the yj plus 1. Yj plus 1. You see from the yj, not the midpoint, from the initial point of the interval, plus the whole step. And we do a straight line using the slope at the midpoint. So this is called the midpoint formula. The midpoint formula to get approximate solution for the initial value problem has the local discretization error. This is a higher order, right? Instead of h to the first power, it is of the order h squared. So after you see the algorithm, and then we can look at the picture, how it's done. So midpoint method with this picture is relatively easy to see. That suppose I do one step from tj minus 1 to tj. This is just a one step. We know this interval, this is one step, right? With interval length being h. So that means the midpoint will be half of h. So the midpoint, which is this tj minus 1 plus half of h. So you get this one. So that midpoint we're going to use at this t, that is the previous t plus half of h. So we do half a step using Euler's method. Simply Euler's method, from here to a tangent line, and then get using the tangent line to get the y at this midpoint. So that's this. Simply Euler's method with the step size half of h. So we see that. And then you get the y at the midpoint. So that's the y at the midpoint. Use that y, let's use that y to evaluate the slope function again. You see this is our t, which is half step from the initial t. That's the y at this midpoint. So we have t at the midpoint and y at the midpoint, right? Both are there. So we're ready to calculate the f, the slope function at the midpoint. So use the t and y, we get the slope at this midpoint. So once we get the slope of the midpoint, then we use that slope, but construct a line passing, we construct a line with that slope, but pass through the first point. So we get a straight line approximation. So let's use this slope at the midpoint because that's the f function value at the midpoint, and pass through this point. So we know this point has to be passed through with that slope, so we can easily find a line. So you see, this is the line with that same slope, right? That means this line is parallel to with that slope f at the midpoint. So this method is called midpoint method because we eventually constructed a line using the slope of the midpoint. And this line gets to here. And we use that, this newly constructed line to predict the y at tj. So this is our yj. So we see that this way we constructed a yj which is better than the one-step Euler's method, right? If you go from this point using the slope at that point, you just go one step forward. And that's a very simple, straightforward Euler's method. We can get this yj. However, using the midpoint formula, we get yj here. That is a better approximation. However, the work is more. How many times you evaluate the function f? We call it slope function, for example. How many times do we evaluate? Twice. Because if you look at the formula, you see, you go half step. You have to get the y at the the y coordinate of the midpoint, right? So that's already one time evaluation of the f. The second time, after you get this y, you want to evaluate this. This is the same y. So this midpoint, the slope at this midpoint, that's the second time evaluate the function f. That's the slope at midpoint. So to arrive at the midpoint using half step, we use slope at the initial point of the interval, and then slope at the midpoint, then twice evaluating the function. So that means more calculations are done in the midpoint formula, but the accuracy is better. So it's h squared. Now, we're ready to look at another method. So this, some implementation program. So another method, which is also second order, local discretization error and global discretization error. So this method is called Green's method. This method, if we look carefully, then we can see how many times we evaluate the slope function. We can see during the implementation, the first time evaluate is the slope at the initial point of the interval. And then you do one whole step, Euler's method. So let's try to imagine the process. So again, just think of one step from Tj to Tj plus 1. Okay, so of course you can continue to do another step, right? So we only focus on one step. So in this one step, from Tj to Tj plus 1, what we start is from Tj yj. So here is the Tj, this is the yj at Tj. And use that first point, and we get slope at this point. And then use that slope. Once we know a slope, then we construct a straight line that go whole step forward. You see the whole step. So it's just the Euler's method, the whole step. Okay, go. Actually, we should go here, right? That's just the one whole step. Okay, so we erase we don't worry about the next step. So we just examine one step. So whole step, what do we get? We get a yj plus 1. This is exactly Euler's method. Yeah, nothing but Euler's method. So, but we will not stop here because otherwise this is Euler's method. We know the order for local discretization error, right, is not high. But then we want to improve this result by using, okay, we want to, this y star, you see, with this endpoint, we can find the slope at the endpoint. So that means this endpoint, this is the y we just found using the whole step Euler's method. So we can find slope at this point. So once you get some slope at this endpoint, slope of the curve, because the curve, right, although we didn't draw the curve, so it is somewhere, then we try to imagine a curve that, yeah, somewhere maybe close or maybe not. So actually, then we know that there is a slope, which is approximate slope to the curve. So yeah, if we can find the slope of the curve, yeah, approximate slope of the curve at the endpoint, which is this one, then we have two slopes. You see slope at the initial point, and after I get the endpoint y value, y coordinate, I can find slope at the endpoint. So with the two slopes, let's do the average. So the average will be just simple average. So K1 is the slope at the initial point. K2 is slope at the end point of the interval. And then average slope. So if we use that slope and construct a straight line approximation passing through the initial point, then we get this algorithm. This is a Green's method. It's actually a weighted average of slope values, right? Slope at the beginning, slope at the end of the interval. And then we use the average slope to hopefully improve the accuracy of the approximation. So the order of Green's method is the second order. So let's look at the picture. It's now easier to understand. In one step, you see, from the current t to the next t, and the y, corresponding y at the current t is already calculated or known. So we have the current t and its corresponding y value. In one step, that is, if you move one step forward, you want to find the y corresponding to the next t. So our goal is to find the approximate y value that corresponding to this next t value, tj. So how do we find that? So of course, if you go simply one step forward using Euler's tangent line approximation method, right? You get here. So that is one step. You get yj already. That is Euler's method. If you stop here, then that's just exactly the Euler's method. But we don't stop here because after we get this yj from Euler's method, we use it. So we use this tj, yj, we calculate slope. That is the slope of the solution curve. For example, although the solution curve, for example, this is our bold-faced solution curve, right? So the slope at this point, tj, yj will be, well, if we look at the exact solution curve, will be like this, right? The tangent line, the slope will be like this. In pink, indicated by this tangent line. So we want to find slope. But since you are using approximate y, so your slope is also approximate. So we get some slope at this. So we get the approximate slope at the end point of the interval. But now what do? We know the slope at the initial point, slope at the end point, then to the average. So then we will have slope here for the first Euler's method, and then to the average. So then that will be the slope for this line. So we use the average of the two slopes, construct a new line that passes through the first point with the slope, which is average of the previous two slopes. And then that's called Quine's method. This method will arrive at a value. And this value, as you can see, it can be a better approximation than using simply the Euler's method. Just to compare the approximate solution with the true solution. So this has a higher accuracy. So that's the idea. So Quine's method, if you look at this method just one more time, Quine's method, you see how many times we evaluate slope at the beginning, and then one time evaluation of the slope, a second time evaluation of the slope function twice, right? And then do the average. And then using that slope passing through the initial point, then construct a line. Use that line to approximate the y at t j plus 1. That is, use that slope to predict the upcoming y. Okay, so this is a Quine's method, but this method give us a hope of getting higher order numerical methods for solving initial value problems. And what is the inspiration is that if we invest in more work and get better approximation to the slope and using weighted average of slopes at different locations, then we can get highly accurate numerical method for solving the initial value problem. So that leads to the fourth order Euler's method. Fourth order Runge-Kutta method. So the general form inspired by the Huygens method, we just write it as, so the next y value is equal to the previous y value. That means the y at the previous t, right? This is just the one-step method. One-step method. So from yj to get yj plus 1, and the interval is just one step. You see, this is a one step that yj corresponds to the y at tj. So yj plus 1 is the approximate solution at tj plus 1. So we certainly assume we already know the yj. How do we get the yj plus 1? So how do we get the y value at t j plus 1? This fourth order Runge-Kutta method assumes a form like this. So that is very similar, right? If we think of the Huygens method, this h is still here, the half of k1 plus half of k2. See, but this is instead of half, we allow the coefficients to be other weights. Yeah, it doesn't have to be 50-50%. So we can allow more points. That means the Rm are the weight coefficients, and Km are the slope functions evaluated at different locations of the interval, the time interval. So the weight function will add up to 1. So here is the specific Runge-Kutta method, which has the fourth order. So how many times we evaluate the slope function, we can see the step 1, evaluate slope at the beginning point of the interval. And then we go half step, right? So this is actually the Euler's method to get the y at the midpoint. So as you can see, this is the approximate y value at the midpoint by Euler's method. And after you get this y at the midpoint, then you can immediately find slope at this midpoint. So that's another term of evaluation of the slope function. Whenever I say slope, that means, actually approximate slope of the solution curve. Yeah, the unknown solution curve. So then after we get the midpoint, we can calculate again. You see the fashion is very similar because we construct another line from the beginning point, still half step, using the slope at the midpoint instead of slope at the first point. So just to use slope of the midpoint, we go half a step from the first point and do another evaluation of the slope at the midpoint. So you see this slope at the midpoint twice, but different approximations for the slope at the midpoint. So next one will be slope at the end point of the interval. You see Tj plus one whole step, H. And that is from the initial point of the interval, go a whole step forward using the K3. You construct a straight line. So you go all the way to the end point. Use that end point, you get slope again. So let's summarize. This is a slope at the initial point, slope at the midpoint, and again, another approximate slope at the midpoint. This is the slope at the endpoint. So 4 times evaluation of the slope function at these multiple locations. And then afterwards, this is weighted average. You see, weighted average, because of 1/6 plus 1/3 plus 1/3 plus 1. Yeah, so all these weights, right, they add up to 1. The weight coefficients together is 1. So this will be approximate slope. This quantity will be the value we adopt for that line that will pass through the first point with that slope, which is represented as average of the 4 different slopes. And then we want to get a nice line just in one step, right? Pass through the first point with that slope and one whole step. Then we construct such a straight line. So this straight line has that slope. So this is our construction. And this method constructed in this way is actually a generalized version of the Green's method. And it has a special name, Runge-Kutta method, and it has a very high order of accuracy, or H to the 4th order. And this shows starting from here, and first time evaluation of the f, the slope function. Second time evaluation of slope function of the solution curve. And third time, that means after we get slope, we evaluate again using the K2, right, to get K3. That's the third time you evaluate the f. And then there's another time, once you get the endpoint, you get a slope at the endpoint. So after you get 4 slopes and do the weighted average, and then use that weighted average as a slope to construct a line from the first point. So then we will get approximate solution. So this picture, just to make you understand easily how we construct a line with the weighted average of those 4 values of the slopes. And then in whole step, and then we use that line to predict the next y value. So such a y value is called method approximated by Runge-Kutta method of 4th order. 4th order can be verified if we we check using our analysis method. Okay, that's all for now.